Good evening, ladies and gentlemen. Welcome to your Learning Target 12 video. This is video 1 of 3 talking about different types of reaction rates. So in Learning Target 12, we're going to discuss 3 different types of reaction rates that we need to know about: average rate, instantaneous rate, and initial rate. So this is again going to be 1 of 3 videos. This one's going to discuss average rate. Let's review what we talked about in Learning Target number 11. We defined reaction rate as the change of concentration of reactants and products per second. Excuse the train. The units we use to express rate of reaction is moles per liters seconds, or moles per decimeters cubed seconds to the negative first power. Remember, when I've got an exponent that's negative, it means it's in the denominator of a fraction. So if we think about the definition for reaction rate, the definition for average reaction rate is exactly the same thing. The average reaction rate is a measure of the change in concentration of reactant or product per a given amount of time. So here's the equation for that. And you'll see here that the average rate is the change in concentration. Remember, the symbol delta means change, divided by the change in time. And if I state this more explicitly, it's the final concentration minus the initial concentration divided by the final time minus the initial time, and most of the time the initial time is 0. So if we were finding the average rate of reaction for a gas, we would change the delta C here to delta V for volume. It would be basically the exact same equation, but we'd be talking about the volume of a gas rather than the change in concentration of an aqueous solution. So the next part of this video is going to go over a practice problem. So here's our practice problem. It says, in a chemical reaction of calcium carbonate with hydrochloric acid, 0.25 grams of carbon dioxide was generated in 60 seconds. We're going to deduce a balanced chemical equation for this reaction. Good practice there. And then we're going to calculate the average rate for the creation of carbon dioxide in moles per second. And notice here that I don't have moles per liters per second because we're talking about how many grams of carbon dioxide. So we're going to just convert grams to moles. So here we go. Step 1, deduce the balanced chemical equation. So I got my calcium carbonate, which is going to be CaCO3. And I'm going to add to that some hydrochloric acid. And it's going to be a double replacement reaction. And when I say double replacement, I remember double replacement is AX plus BY. We'll make some AY plus BX. Good review there. And I'm going to have my calcium go with my chlorine. And I'm going to have my hydrogen go with my carbonate. And then I'm going to check my charges. I look at my periodic table, realize calcium's a +2, chlorine's a -1, hydrogen is a +1, carbonate is a -2. Therefore, I need 2 chlorines to match with every 1 calcium, and I need 2 hydrogens to match with every 1 carbonate. And by the way, I get that charge for that carbonate off a polyatomic table. Next thing I'm going to do, though, is I need to remember that carbonic acid is incredibly unstable and it will immediately decompose. And when I say immediately decompose, this is where we're going to get our carbon dioxide from. Carbonic acid is going to immediately make water and carbon dioxide. And I'm just going to cancel this out because these two are my new products. Double checking to balance, I got 1 calcium 1 calcium, 1 carbonate. Remember, that's in parentheses. It doesn't have to be, but it helps you remind you it's polyatomic. 1 carbonate, which has 3 oxygens. 1, 2, 3 oxygens. 1 carbon, 1 carbon. Then I've got here 1 hydrogen and 2 hydrogens here. So I'm going to have to throw a 2 out in front. And then 2 chlorines and 2 chlorines. So even though I went back and balanced here, this is an irrelevant thing that I had to add that coefficient of 2, but the correct balanced equation is really important. Next thing is that average rate. And remembering that my average rate is going to be, I don't want to call it R for rate, it's going to be change of concentration over the change in time. And the concentration is going to be proportional to the number of moles created, and we'll just pretend it's 1 liter. So if I find the moles of carbon dioxide and divide that by the unit of time, I'll get the rate. So I'm going to get that molar mass of carbon dioxide. I got 1 carbon that's worth 12 grams per mole. I got 2 oxygens. That's going to be worth 16 grams per mole. I'm going to add those together, and it's going to be 44 grams per mole. And so then I'm going to get my grams of carbon dioxide, 0.25 grams, and I'm going to have 1 mole divided by 44 grams. And when I put that into my calculator, move me, I get 0.0057 moles. Last thing I got to do here is divide that by time. We're going to pretend that that's moles per liter because we're going to assume we have 1 liter of solution. My change in time is 60 seconds. We'll assume time initial 0, so 60 minus 0 is 60 seconds. So I'm going to divide this by 60. 0.0, paying attention to those sig figs. And when I do this, I'm going to write the answer in scientific notation because it's a very small number. And you're going to see a lot of these numbers that we're going to calculate are incredibly small. And the number we get is 9.5 times 10 to the negative 5th. And I'm going to say moles per liter seconds. And that is how we calculate the average rate for this particular reaction. And it seems so nice, simple, and straightforward, but for this reaction it is because it's called a 0 order reaction. You're going to find out why that's important in the next video when we talk about instantaneous rate. So this is part 1. Over and out.